Hi, welcome to my extensive playthrough video about Orbit 3, the new Chaos module by Joranalogue Audio Design. Orbit 3 is a double-scroll Chaos oscillator, and it uses a system based on a type of strange attractor called Schwa's attractor to create oscillations. Orbit 3 can be used as a near sine wave or as a square wave VCO, as a noisy sine or a noisy square wave, as white or colored noise. You can use it as a modulator for your system with chaotic or periodic and stable fluctuations, as a random gate or trigger, or as a stable clock. You can use the chaos outputs to modulate filters and effects in stereo, or to create off-kilter drum beats. You can use the EP output to open up VCAs, sync other VCOs, or create stuttered modulation. You can sync Orbit 3 in both low or audio mode to just about anything, from slow-moving control voltages to VCOs. You can self-patch to create waves that resemble a saw wave or rectified sines. The list goes on, and there's plenty of options to choose from. If you're already overwhelmed or confused, then you're in the perfect mindset to enter the realm of chaos and determinism. I'll try to explain and show you what Orbit 3 is all about in this video, and how you can use the module to create lively tones or modulations for your system. I've written a timing index in the description, so you can skip to the part of the video you're interested in. First, let's listen to some sound examples, and after that, we'll get started with a complete overview of this weird module and a little bit of science history. Let's get started. Orbit 3 is a double-scroll chaos oscillator. It uses a theory first submitted in 1963 by Edward Lorenz that describes a system called a strange attractor or Lorentz attractor. The theory was the result of research about weather patterns. Lorenz was investigating how temperature, humidity, wind speed, and a ton of other variables were interconnected and how they changed over time. All he had to work with was a very old computer and a printer that showed sine-like shapes. The curves he saw were exactly like the ones from Orbit 3, and when he plotted these into a simplified 3D model, the double scrolls became very apparent. There was an orbiting movement around 2 points, and the slightest variation would result in a completely different outcome. This principle was submitted in a paper called The Butterfly Effect, and the equations describing this shape or motion are called the Lorentz equations. In 1983, an American electrical engineer and computer scientist called Lian-Hong Chua reimagined this principle in an electronic circuit that resembles the Lorentz attractor, but implemented in such a way that it could be easily reproduced and used in labs all over the world for research about chaotic systems. The most apparent difference between the Lorentz attractor and Chua's attractor is the way the system crosses over from orbiting one scroll to the other. In the Lorentz attractor we see a figure 8 pattern, and in Chua's system the direction of the movement is the same for both orbits. Orbit 3 is actually based on this revolutionary circuit called Chua's circuit. I found a really interesting video about chaos and the Lorentz attractor on a YouTube channel about maths and science called It's So Blatant. And even though the system invented by Chua is considered to be the opposite of the Lorentz attractor in a unified chaos theory, for the purpose of explaining how Orbit 3 works, the similarities are adequate. I will show you some clips of this video in the following segment. The link to this video is in the description. Let's look at some animations that describe Lorenz's findings. We see an orbiting movement of a virtual particle around two equilibrium points. This isn't a virtual particle like in quantum mechanics, but I use the term because the particle or point doesn't really exist in real life. It's just a solution to the Lorentz equations describing the relationship between three different parameters like wind speed, humidity, and temperature. If you find it hard to grasp, consider a sine wave representing sound. There is no real particle moving around in sine-like shapes. The sine is merely a 2D projection of a three-dimensional pressure wave. It's just easier to work with when we extract simplified graphs from real-life scenarios, even though the jargon might make it a little bit confusing. Now, the solution to the Lorentz equation, in other words the movement of the virtual particle in our system, is well defined and deterministic. This means that when you know the position, direction and speed of the particle, it's perfectly possible to compute the trajectory. While being easy to predict and therefore deterministic in nature, the slightest change or rounding error in any of the parameters results in a completely different trajectory. Now this is exactly what chaos is all about. Chaotic doesn't mean random. It means that the end result is extremely sensitive to small differences in the conditions at the start. On orbit 3, this means that the slightest change to any of the parameters can alter the signal coming from the outputs a lot. Luckily, there are many settings that produce stable oscillations, resulting in something that we can actually use as a VCO with a pitch that actually tracks to 1 volt per octave. Let's take a look at this even more simplified so-called paper model of the Lorentz attractor using a racetrack and a car to understand how non-periodic and periodic or bistable oscillations happen inside this system. Please ignore the numbers and fractions in the video, they are of no importance to us. Look at the car driving around the track. You can see that when the car ends up exactly where it started, you get a stable system with a period or a frequency. In orbit 3, this translates as a stable VCO or LFO with a clear frequency. You can also see that a slight change to the trajectory of the car can result in a motion that never gets back to where it started. In this case, there is no period, and if you would project this movement onto the X, Y and Z axes, you would end up with oscillations that are never exactly the same. Now this is what happens at the chaos outputs on orbit 3 as well. There are settings where the oscillations are stable, and when you patch one of the chaos outputs into a mixer, you'll hear a solid frequency because the oscillations have a fixed period. At other settings, there's never a fixed period, so no stable frequency or pitch, and this will of course sound like some kind of noise. Let's have a look at what all the knobs, switches, inputs and outputs on orbit 3 do. I'll briefly explain every function and every parameter, and afterwards I'll spend a little more time showing and explaining you some patch examples that demonstrate the functionality of this module in the context of a modular system. The stars of the show are of course the chaos outputs. These outputs, labeled X, Y and Z, are the projections of the orbiting motion on the according axes. Due to the orbiting motion, these outputs are similar but never the same and 60 degrees out of phase. The -X, -Y and -Z outputs send out the same signal as their positive counterparts, but inverted, or in other words, 180 degrees out of phase. I found that these inverted outputs make it very easy to modulate a set of filters to get some stereo spread, like I'm doing at this very moment. Orbit 3 is running in low mode, so the chaotic system moves a little bit slower, and I can show you what's happening on the scope. Now the frequency knob does exactly that. It changes the speed of the system, and turning the knob to the right increases the frequency or pitch of the signals at the output. The range on Orbit 3 goes from 22 Hz to 22 kHz in audio mode, and from 2.4 mHz to about 180 Hz in low mode. So from extremely slow up into audio rate. The distribution knob changes the width of the racetrack, so to speak. Generally speaking, this means that the orbits will start closer to the center points, but move farther away. This also means that our virtual particle takes more time to switch over to orbiting the other equilibrium point. The knobs for the negative and the positive equilibrium points change the distance of the center of the orbits from origin, or 0 volts. Turning them to the right increases the distance, so for the negative equilibrium point this makes it more negative, and turning the knob for the positive equilibrium point to the right makes it more positive. Changes to these parameters also change the width of the orbits, and generally the orbits become larger when you turn the knobs to the right, increasing the amplitude of the according orbits and the amplitude of the signal at the chaos outputs. This also influences how much time the system takes to switch over between orbiting the negative and positive equilibrium points. There is no way to bring the two equilibrium points completely together, but it's possible to make the orbits overlap so much that the orbit around one of the equilibrium points almost completely swallows the orbit around the other one. When we look at the signal of the X output on the scope, you can see clearly how changing the settings for these knobs changes the offset of the oscillations. And you can also see how the amplitude of the signal is influenced. The tame and wild switch changes the behavior of the chaotic system, and by switching over to the wild mode, you'll see that the movement becomes less predictable and the tendency of the virtual particle to change from orbiting one equilibrium point to the other one increases. I hope that by now you understand that all of these parameters and settings interact. It's impossible for me to say, this knob makes that louder. Joranalogue Audio Design gave us a sensitive user interface to shape the behavior of this strange attractor, but nevertheless, it is a chaotic system, so little changes to the settings might always have unpredictable results. Luckily, there are a lot of stable settings which produce periodic oscillations we can use as a VCO or an LFO. All of the parameters, except for the two switches, can be voltage controlled. The frequency modulation input accepts bipolar signals and is calibrated to 1 volt per octave in audio mode when you turn the knob completely to the right. So if you send in a pitch sequence, Orbit 3 will track this sequence perfectly. Please note that at some settings the chaotic system isn't completely stable, and while the pitch tracking on Orbit 3 is perfectly calibrated, the system itself might not stay stable across the whole range. Of course, there are settings at which the system actually does stay stable. The frequency modulation knob is a polarizer, so you can invert and attenuate the input. In low mode, the sensitivity of this exponential FM input is increased to 0.6 volts per octave. This is to ensure the complete modulation range can be achieved with input signals going from -5 to +5 volts without having to amplify them first. The distribution modulation input accepts bipolar signals as well. The according knob is a polarizer too, so you can invert and attenuate the signal. Maximum modulation is achieved with -5 to +5 volts. The inputs for the equilibrium points accept bipolar signals too, but the knobs don't turn into polarizers. Instead, the signal at the inputs is just added to or subtracted from the position of the knobs. The reset input on Orbit 3 is cleverly designed and it reacts to about any signal you send into it. You can use LFOs, VCOs, gates or triggers to force Orbit 3 to reset its oscillations. This is useful to create typical hard sync sounds or to synchronize Orbit 3 in low mode to the tempo of your system. You can even use this input to self-patch Orbit 3 to produce stable oscillations at any setting. This patch is explained in the manual, by the way. For this we will use the EP output, which sends out 5 volts whenever the chaotic system is orbiting the positive equilibrium point. It sends out 0 volts when the system is orbiting the negative equilibrium point. You can use this output to self-patch, like I'm doing right now. Let's send in a pitch sequence. So you can use this output to self-patch Orbit 3, like here, or you can use it to sync other VCOs, trigger drums, clock a sequencer, open VCAs, etc. Let's get into some patch examples to hopefully give you some ideas on how to integrate Orbit 3 into your system. There's a few things going on in this patch. First, let's remove the outputs of Generate 3 from the signal. So right now we're listening to Orbit 3 by itself. The EP output is going through a VCA into the reset input. When I remove the signal, this is how it sounds. But when I patch this back in, you can hear a pattern of stable pitches. Orbit 3 is receiving pitch information from Moskwa 2. The EP output is going through a VCA before it's going back into the reset input, and it's being gated by a pattern from Joranalogue repetitor. Let me add the envelope again. Let's listen to what Generate 3 is doing. So this is the core output from Generate 3. And I added the even output through a delay as well. Generate 3 is not receiving any pitch information. It's just being synced by the multi signal coming from the EP output on Orbit 3. Let's listen to the whole patch again. This patch is similar to the previous. Let me remove the distribution modulation first. I have the Z output. That's the top trace on zero scope. And the EP output as well. That's the bottom trace. I have them both going into my MA35 mixer. Let me open up the frequency on the mixer. Let me mute the kick drum for a moment. Let's listen to the Z output only. And this is the square wave coming from the EP out. The green cable is a pattern, once again from Joranalogue repetitor. In this patch, I'm resetting Orbit 3 with the clock coming from Pamela. You can see it as the bottom trace on zero scope. The top trace is the output coming from the -Y output on Orbit 3. Orbit 3 is in low mode. It's modulating the filter cutoff. Generate 3 is going through this filter. I'm modulating the amount of phase modulation on Generate 3 with an output coming from Orbit 3. I'm also triggering an envelope with the EP output from Orbit 3, which raises the pitch of Generate 3. I'm sending in a pitch sequence to Generate 3, and the source for the phase modulation is EVVCO being synced to Generate. The envelope that's being triggered by the EP output from Orbit 3 is also patched into the frequency modulation of Orbit 3. The cables connected to the X and the Z output are going to the even and the odd harmonic input on Generate 3, so they're controlling the level and the timbre of the sound coming out of the full output. Let me remove the phase modulation for a moment. And I can in fact use one of the chaos outputs on Orbit 3 to trigger additional drum samples. And depending on how you have Orbit 3 set up, this can sound really musical, it can sound chaotic or wonky or off-kilter. Let me try the -Z output, it's the only other one that I have still left. In this patch, I self-patched Orbit 3 by connecting the -Z output into the frequency modulation input. I'm creating some pitch variation by modulating the distribution. On the scope, we see the X output, it's the top trace. We see the -Z output, that's the bottom trace. They are going through a pair of filters, band left and right on the mixer. What we're listening to right now is only the Y output. It's going through a filter that's been modulated by an LFO, and that is going into a stereo delay. Let me add the X and the -Z outputs again. Let me add some drums to this. These are triggered separately and have nothing to do with the functionality of Orbit 3. This patch is almost the same as the previous one. The only difference is that I removed the distribution modulation to create pitch variation. Instead, I'm syncing Orbit 3 to Generate 3, which is receiving the pitch information. The output of Generate 3 is not going into the mixer, so we're only listening to the outputs of Orbit 3. And you can hear how Orbit 3 syncs nicely. Let me move some knobs. And of course, by modulating these parameters, you get additional variations to the sound. I think I'll finish off the video with this drone in which Orbit 3 is modulating absolutely everything. I hope you learned something and that by watching this video you can make a little more sense of what Orbit 3 is all about. Thanks for watching.